This podcast is about types of acids and bases and how we categorize them. So there are three basic types of acids and bases, and those are the Arrhenius, Bronsted-Lowry, and Lewis acids and bases. And these are done in order of history of how acids and bases were defined in history. And the first way that people talked about acids and bases was the Arrhenius definition, and Arrhenius said that acids and bases could be defined by their behavior in water. So in water, if an Arrhenius acid was added to water, that would increase the protons in the water. And an Arrhenius base would have hydroxides, and it would increase the hydroxide concentration in water. And still, we use this definition a lot because most of the common acids and bases that we talk about fall into these categories. So, for example, acids that have protons in the front, HCl, H2SO4, we call them Arrhenius acids. And bases that have hydroxides, like sodium hydroxide, magnesium hydroxide, those are Arrhenius bases. So why wasn't this definition good enough to last? The problem with it was that some bases, and the big one was ammonia, which is NH3. Notice it doesn't have a hydroxide, so they couldn't fit it into this category. So that required a new category for acids and bases. And that category, the next one, is called Bronsted-Lowry, and it is defined as an acid is a proton donor and a base is a proton acceptor. So again, if we look at what happens in water, if we have an acid and we put it into water, so the acid is the proton donor and it's going to take its proton here and give it to water. And that's going to mean NO3 without the proton, and then water has gained the proton and it is H3O+. So a base is going to accept a proton. So here the NH3 is a base and it's a proton acceptor. It takes a proton from water and it gives NH4+, and it leaves the water to be hydroxide. So we can see why it acts as a base, even though ammonia doesn't come with its own hydroxide. So notice that water can do both things. It can act as a base when it's with an acid, and it can act as an acid when it's with a base. So the word we use for that is amphoteric. Water is amphoteric, and it can act as an acid or a base depending on the situation. So for this next list, pause your video and go through and try to complete the reactions looking at the acids or bases and figure out what they are going to do with their protons. And ammonia is the only weird one. So ammonia picks up a proton, it accepts a proton, but the rest of them are acids. And this is what they do with water. The last definition of acids and bases is Lewis. And it doesn't even focus on protons at all. The Lewis definition says that a base is a lone pair donor and an acid is a lone pair acceptor. And remember when we did Lewis structures, when we were drawing structures, we talked about lone pairs, and they are the pairs of electrons that are not part of a bond, just sort of stick out. So those are involved in acid-base reactions in what we call Lewis acids and bases. The best way to learn these is just to look at examples. So the first example is boron trifluoride and ammonia, and this is what's going to happen. The product, when we put them together, is called an adduct. So BF3 and ammonia gets together, and the trick here is to look for the lone pair. So ammonia here has the lone pair, and it's going to use its lone pair to make a bond with boron. So ammonia is the lone pair donor, so it's the base, and boron is receiving the lone pair, so it's the Lewis acid. And then a new bond forms, and the new bond is right here, and it's formed from the lone pair, and this is called a Lewis acid-base adduct. The next one is sulfur dioxide in water. Again, looking for the lone pair from the Lewis base, and it forms a new bond to make the adduct. And also metal cations can act as Lewis acids with water. So sodium plus water, again, the lone pair makes the new bond, and the lone pair is the Lewis base, and the sodium is the Lewis acid. Okay, strong and weak acids and bases. So what is a strong acid? A strong acid is defined as an acid that completely dissociates, which means all of its protons come off. So it's going to lose all of its protons in a reaction or in water. And the 5 strong acids that you have to know are the halogen acids HCl, HBr, HI, nitric acid, which is HNO3, and sulfuric acid, H2SO4. A weak acid is an acid that does not completely dissociate or it does not lose all of its protons. And the weak acids that you need to know are HF, acetic acid, and phosphoric acid. So what happens is, instead of all of the protons coming off, a lot of the protons actually stay together with the acid and they make the acid weaker. It's not as strong because remember that an acid is, its strength is determined by the number of protons free in solution. So a strong base forms high concentrations of hydroxide. So the hydroxide bases are all strong bases. Sodium hydroxide, magnesium hydroxide, any hydroxide base, lithium hydroxide, potassium hydroxide. I did not list them all here. But all of the hydroxide bases are strong. And the weak base that you have to know is ammonia. It does not form a lot of hydroxides, not as many, so it is weaker. And these you have to memorize. So we are going to write balanced equations for strong and weak acids in water. And the way we're gonna look at them and say, okay, this is a strong acid. This was not on our list. It is perchloric acid, but it is a strong acid. So we are going to write a one-way arrow because everything is going to get dissociated. And if it's a weak acid, we're going to use a double arrow, reversible arrow. So pause your video and finish this page and then play it again and check. So notice for acetic acid, it is a weak acid, so we've drawn a reversible arrow here.